So we're good. So this is module 3 of HVAC systems. We're going to talk about cooling systems and equipment. Basically, you want to get a thorough understanding, or at least a working understanding of what is cooling and how we accomplish it using refrigerants and the refrigerant cycle, how we use that refrigerant cycle to create the chill water cycle, and what are some of the equipment that we actually use to do that. So cooling, quite simply, as I said, is the transfer of heat from one substance to another. So a couple examples: you blow on your coffee, you're transferring heat from the coffee to the airstream that you're blowing across it. That's called that's a sensible heat transfer, primarily by convection. You drop ice cubes in a drink, you're going to be doing latent heat transfer, conducting that heat into the ice cube and making it change state. Substance that gives up its heat is considered to be cooled. Substance that takes that heat and removes it is the coolant. Most common method that we use to remove heat from a building, we pass air across a cooling coil. That can be a chilled water coil or a refrigerant coil like the one in the picture. So a coolant can be a liquid that never changes state, that just changes temperature, or it can be a refrigerant. We'll get into that in a little bit. How about right now? Refrigerant is a coolant that picks up heat by evaporating to a gas at low temperature and pressure, gives its heat back up when it condenses to a liquid. So you got change of states, you got latent heat transfer going on as opposed to just sensible, like in a liquid cooling coil. So what do we want in a refrigerant? We want it to be non-corrosive. You don't want it eating through the pipes that we're using to convey it. But even more importantly, it needs to be able to change between states at temperatures and pressures that we can work with. So water has been used, carbon dioxide, ammonia, all been used as refrigerants. Most common refrigerants, though, are the fluorocarbons. Like a dirty word anymore, but that's still what they're called. They come in 3 basic groups. The CFCs, which are kind of the granddaddy, R12, R11. Some of us still remember those. Those were phased out in 1996. They're no longer legal to manufacture them or import them. They were replaced by the HCFCs, the hydrochlorofluorocarbons. So that's your R22s, R123. They are being phased out as well. We're not going to be able to make them or import them after 2030. HFCs were introduced in anticipation of HCFCs being phased out, and as technology improves, they're already thinking about phasing these ones out and replacing them with something called hydrofluoroolefins and CO2. I mentioned ammonia before. Ammonia is a very good refrigerant. Actually, it's best suited for industrial and heavy commercial applications. I don't know if they got used down at Boston Sword, but it wouldn't have surprised me if some of their stuff was ammonia driven. It's got some good qualities to it. It's very efficient thermodynamically. So that leads to better heat transfer, which allows for smaller piping and equipment sizes, and also reduces your operating costs. And it's also one of the most environmentally friendly refrigerants. It occurs naturally in nature. You don't have to manufacture it. Has 0 ozone depletion potential and 0 global warming potential. So it makes the green folks very happy. However, there is one big con about it. It is toxic as hell. So anybody who's got ever got a snoot full of even the diluted ammonia, you don't forget it too quickly. So it really needs to be used where you have professionals on site who can deal with it. It's not really suited for residential or light commercial at all. So let's talk a little. Any questions so far on refrigerants? Not yet. Okay, good. Refrigeration cycle. So we all know that in nature, heat flows from a higher temperature to a lower temperature. Basically, if you leave the door open in the winter, your house is going to get cold. All that heat's going to flow out. It's going to basically achieve equilibrium with the exterior, right? Mechanical cooling systems all use the refrigeration cycle, which basically pushes heat in the reverse direction from a lower temperature to a higher temperature. So that, just like, you know, rolling a boulder uphill, it takes work to go from a position of lower potential energy to higher. So we have to invest energy in that. We put that energy into a process called the refrigeration cycle, and typically that's most of the energy goes into that when we drive the compressor with an electric motor. That refrigeration cycle basically consists of a closed hermetic loop with a refrigerant, usually from the fluorocarbon family. So this loop basically picks up heat from the environment or whatever medium that's being cooled, chilled water, for example, and ultimately rejects it to atmosphere. Or if there's another process that can use that waste heat, we'd basically insert it into that process. One form of energy recovery. Refrigeration cycle has 4 stages. First stage, the refrigerant enters the compressor in a relatively cool state as a gas, and it gets pumped up in pressure. And as we know, when you pump something up in pressure, if you don't let the volume increase, you're also going to increase the temperature. So it leaves as a hot, high pressure gas. From there, it goes to the condenser and it gets cooled. And in that cooling process, it condenses to a liquid, hence the name condenser, but it's still at high pressure. So that high pressure pushes it down through the metering device known as a thermal expansion valve. And as it goes through the tiny orifice in that valve, it gets atomized into a mist, and then it gets sent into the evaporator. And as the name suggests, once it goes into the evaporator, it evaporates back into a gas, and in so it takes in heat from whatever medium is passing over the exchanger, and that low temperature gas then gets sent back to the compressor, and the process repeats. So for those 4 stages of the cycle, you have 4 essential components. Stage 1 is the compression stage. So a couple of different examples. On one on the left would be a reciprocating compressor. We have a couple of scroll compressors on the right. The condenser, where we reject the heat to the atmosphere. Essentially a big coil and some fans. On the left, you have a typical residential condensing unit that would also contain a compressor inside it. On the right, there's a commercial condensing unit. So that's basically just a big coil and a row of fans. And then this one here is a water-cooled condenser. So like I said, we can reject that heat not only to the atmosphere or to the air, but we can also reject it to a water loop. From the condenser, it goes to the metering device or the expansion valve. And that just basically meters the refrigerant into the evaporator coil. And then on into the evaporator coil, where again, it changes state back into a gas and sucks heat out of the airstream. So this on the left, it would be a typical residential it's called an A coil for obvious reasons. On the right, you see something that's more typically found in an air handling unit like we would have put on a roof. And you can see here the distributor where the refrigerant comes in is a very fine mist in these small tubes. And as it expands and evaporates, the tubes get larger until it's collected in a header and brought back to the compressor. Any questions so far on the refrigeration cycle? Pretty dry stuff, huh? You still awake, George? All right. So this is what it looks like graphically. Here's the compressor. Basically, this is where we put in the driving force for the system. We spend most of our energy. There's also a little bit of energy in the condenser fan and the evaporator blower, but that's compared to the compressor very small. Again, we take the low pressure, low temperature gas, pump it up to a high pressure gas, condense it to a liquid, still at high pressure, sprayed through the metering device into a mist. So that liquid mist evaporates to a gas and goes back to the compressor over and over and over and over again. What's this look like in real life? Well, typical window air conditioner, you have a compressor on the outdoor section along with the condenser coil. And then just inside, you'll have your thermal expansion valve where the liquid comes in and gets misted into the evaporator coil and repeats. Same thing happens in a, wrong one. Same thing happens in a split system, typical residential split where you have an outdoor condensing unit. Basically, they've just taken this box on the left and split it into two pieces. Compressor and condensing coil, condenser fan outside. Inside, you have your expansion valve, metering device, again through the A coil and back out. So chilled water systems basically work on the same principle as the air side systems, like the residential systems we just looked at. The difference there is basically all this refrigeration cycle takes place inside the chiller. Chiller uses that cycle to remove heat, not from the environmental air, but from a chilled water loop. And that water loop in turn is used to move the heat back to the chiller from the spaces, usually via air handling equipment. Although sometimes via things like radiant cooling panels and those kind of or chilled beams, things like that. Then basically the chiller will reject the heat into the atmosphere if it's an air-cooled chiller, or into a separate water loop, which conveys the unwanted heat to the exterior by means of a cooling tower. So another graphical look at it. Inside the dotted line are all the components that you'll find in the chiller. So compressor with a motor. Typically, these days, chillers are driven by VFDs. Your water-cooled condenser, and that condenser water loop goes to the cooling tower, rejects heat out the cooling tower, comes back about 10 degrees cooler. Typically, you're going to see 90 to 100 degrees going up to the tower, and again, 80 to 85 degrees coming back in that range. Refrigerant loop here, we just talked about that plenty of times. Compressor, condenser, expansion valve, evaporator. And then on the chiller, the evaporator is also basically a water-cooled evaporator, and you're transferring heat from the refrigerant loop into the return water and sending it out. Typically, your primary supply is going to be in the 44, 45 degree range, and it's going to come back about 10 to 12 degrees warmer. So the heart of the refrigeration cycle is the compressor, several different types. The granddaddy of them all is the reciprocating compressor. Basically, just it looks like a piston-driven engine. It's got pistons in it, and that pulsed flow of gas results from the positive displacement of the pistons. So it's not a continuous flow. It is actually pulsed down through the system. Typically, you're going to see these in capacities up to 200 tons. Unfortunately, they are noisy, and because they are reciprocating, they do create quite a bit of vibration. Most manufacturers have phased these out in favor of other designs. So let's get a little animation here. If I can reshare my screen. Let's see. That one. You got an animation coming up?
Yep, there it is.
You got it? All right, I should be back to the slideshow. Next type of compressor we want to talk about is the centrifugal compressor. The centrifugal compressor allows for continuous flow of gas. It is purely rotational motion, so the vibration is minimal. Typically, you're going to see these 200 tons and up, rather. And the latest thing that's come along for centrifugal designs is the maglev bearings, the smart chillers, they're called. So basically that does away with the oil lubricating system and increases efficiency considerably. Now we get another animation to go for that one. Too many screens. All right. See how these suckers work. If she doesn't put us to sleep.
We don't have any audio for these.
No audio?
I can see him, but I can't hear him.
All right, I might have to animate it myself. So basically, there's three parts to a centrifugal compressor: the impeller, the diffuser, and the volute casing. Larger compressors actually have multiple impellers, so you have multiple stages. So basically, all the impeller is like you've seen these for pumps, the same thing. It's a disc that's driven at very high speeds, sucks the refrigerant into the center and forces it to the exterior by centrifugal force. So basically, the impeller is transferring its energy into the vapor, but even though it gets to high velocity, it doesn't make high static pressure. So that's what the diffuser's for. They slow down the vapor with the diffuser to basically turn the velocity pressure into static pressure. So once it comes in and goes through the diffuser, it's collected in the volute casing and conveyed to the discharge. In order to control the capacity, a couple ways. One of the ways is inlet guide vanes. So when they're fully open like this, you're at full capacity. And then when you start to close them, you reduce obviously the cross-sectional area and also impart some rotation to it, so that slows down the capacity. The other way is obviously with the VFD, which is what is probably more common now than inlet guide vanes. And that's pretty much it for those. All right, do that one after. Go back to the PowerPoint. Okay, I don't know what happened. Do we have sound on the first one, guys? No sound on the first one either.
No, there was no sound.
Oh yeah. Wait a minute. I may have just fixed that, but hopefully you got the point on how that thing works. All right. Third type I want to talk about is rotary screw compressors. So this combines the positive displacement characteristics of the reciprocating compressor with the continuous flow characteristics of the centrifugal compressor. So again, it's purely rotational motion, so the vibration is much less than a recip. These just because of the way they're designed, they do tend to make kind of a high pitched whine, but pretty low vibration. 50 to 500 tons capacity typically. And because maglev centrifugals are basically have wider range of capacity, these are kind of being displaced as well. All right, let's try this thing again.
MEP Diesel and Turbo manufactures tailor-made process gas screw compressors for customers, a modular system of tried and tested components guaranteeing the utmost reliability. Depending on its size, a compressor stage can suck in and then compress volume flows of between about 200 and 100,000 cubic meters per hour. All screw compressors operate according to the basic principle of a positive displacement machine, whose key element is a pair of spiral rotors. During operation, the rotors turn and the spiral teeth mesh together, forming chambers between the rotors and the casing wall. Rotation causes the chambers to move from the suction or intake side to the compression or discharge side. These chambers are connected to the suction nozzle via ports. As the chambers enlarge, they are filled with gas flowing in through the nozzle. To understand the compression process better, let's look at an individual chamber. It enlarges, is filled with gas, and then closed by a circumferential edge in the casing. The rotors now transport the gas to the discharge side, where the chamber shrinks and the retained gas is compressed. Let's view the process again, this time from below. Once the gas is compressed, the chamber reaches another port connected to a discharge nozzle, and the gas flows out.
So again, in as a cool, low pressure
In fact,
gas,
all the chambers between the two rotors are being filled and emptied continuously. This means that with a screw compressor, the compression process is more or less ongoing. The design of a screw compressor combines the advantages of a positive displacement machine with those of a rotating machine, making this type of compressor suitable for a very wide range of applications and process gases. MEP Diesel and Turbo has been developing and constructing process gas screw compressors at its Oberhausen location since.
Last but not least, we can talk about the rotary scroll compressor. These are probably the most common type of compressor you see out there, all residential systems. These go down to half a ton and up to about maybe 20 tons or so, typically. They do also do continuous displacement. There's only one moving part, which is an eccentric rotor. Because it is eccentric, it does have some vibration to it, almost like the vibration you get out of your phone, because there's a little rotating eccentric thing in there, but much less than a reciprocating compressor. So typically half a ton, do I say 20 tons? So 25 tons, probably the biggest single scroll compressor you're gonna see. And then they get combined into multiple compressor systems for larger tonnage. Typical applications are residential and light commercial. Split systems, packaged rooftops all use these. And last animation of the day, guys. by that motion, I'll be that tendency to want to wobble. There's no goal in the goal. I rotate and install it's basically creating chambers, which is the top. Sorry. Cool gas could be the top, but not that's bottom. All right, I don't know what this.
Okay, it's almost 2020. If you're still using regular toilet paper, what are you doing? You need to get clear air in your life, okay? It'll change your life. This is so amazing. Instead of wasting money and hurting the environment with...
Back to it. So those are the 4 different types of compressors that we're typically going to come across in our business. Let's talk a little bit about air-cooled chillers. So an air-cooled chiller, basically you don't have the cooling tower. Instead of the water-cooled condenser, you have an air-cooled condenser. These are fairly common in the type of work that we do. They are much less expensive to install than a full water-cooled system. You can see the refrigeration cycle's the same. Coming out of the compressor, hot gas into the condenser where it gets cooled and condensed, and then sprayed into the evaporator where it goes back into a gas and gets sucked back into the compressor. So basically, long story short, an air-cooled chiller, your condenser is a refrigerant to air heat exchanger. Here you can see your evaporator bundles in blue, scroll compressor, and then the air-cooled condenser on top with coils on each side and fans on the top. Couple of real pictures. This one happens to have a pair of screw chillers, the screw compressors on it. This one on the right has a series of, looks like 3 scrolls. So this is probably 75-ton chiller. On the water cooled, we saw this picture before, but just to revisit it, your condenser is water cooled. So you're actually rejecting to another loop. You do have another set of pumps you have to deal with, another set of piping. That cooling tower water does have to be treated typically. If you're going to be using your cooling tower in the winter, you have to have basin heaters. There's a lot that goes into a water cooled system. Why do we do it? They do run very efficiently compared to air cooled systems, even with the additional pumping and piping. That water to water heat transfer is much more efficient than water to air. Components of a centrifugal chiller, kind of a cutaway. You can see where the compressor takes in that gas, sends it to the condenser, where it condenses to a liquid, goes through a metering device into the evaporator bundle, where again it changes state back into a gas, and the process just repeats itself through the machine like that. This is what a screw chiller would look like. So you can see the different configuration for the compressor. They typically look like, something out of a submarine. Other than that, they're exactly the same. Here's your thermal, good shot of the thermal expansion valve, letting the liquid refrigerant into the evaporator. The evaporator tube that's how you know it's the evaporator side. It's going to be the side that's insulated. Let's talk a little bit about cooling towers. George, you want to take this part?
Absolutely.
George and I have had a lot of fun with cooling towers recently. So a cooling tower simply rejects the heat from the condenser water loop to the atmosphere. Typically, your water is going to enter the cooling tower at about 100 degrees or so and come out around 85, 88 degrees. How does it work? We basically spray the warm water over a medium called a fill, and then it just basically cascades down into the sump. Why do we have a fill? Just it basically slows the water down, gives it more time to give up its heat, essentially, by evaporation. Again, if you have to run the thing year round, you're going to need to have heaters in your sump to keep it from freezing. From the sump, the water gets pumped back to the condenser, and you repeat that process. A couple typical tower types we will encounter are induced draft and forced draft towers. So induced draft towers are called induced draft because we're basically pulling the air or inducing the air to come in through the tower by means of a fan that discharges on the top. A little more terminology. A counterflow tower simply means that the air is flowing in one direction and the water is flowing counter to that, the opposite direction. So here the air is flowing upwards, water is flowing downwards. This is the same idea. This one just has the fill shown in it. So as you can see, you can give up some heat when you create a spray with the water, but if you can slow it down on a medium and let it drip, 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 and get more heat transfer out of it. Cross-flow towers are called cross-flow because the air crosses the water in a crossways motion. So the air comes in left to right here, and the water is coming down. Single-sided, double-sided. Pretty simple. Very simple machines, actually. And that's what one might, induced draft tower might look like in real life. The fill is actually inside, and these are basically mist eliminators, so the air can come in without basically spraying water all over the place. They can get pretty big too, just by comparison. That's what we deal with, but there's people out there who deal with towers like this. This would be a forced draft tower. This is like the tower that we have down at Long Wharf. That's centrifugal fans blow the air into the tower, forcing the draft, in other words, forcing the air up through the fill and out through the top. So those fans could be either centrifugal fans like shown here. Could be a single fan, can be as many as 5 or 6 fans, depending on how big the tower is. Every now and then you'll see axial fans for induced draft, forced draft towers. Not quite as common though. I'm not sure why, but more often than not, you'll see the centrifugals. So that's pretty much all I have to cover today. Any questions thus far before we wrap this up? All right. I guess that's a big no.
Hey, Mark, I actually got one question for you.
Go.
So with chillers, I've noticed that between the evaporation tube or section and then the condenser section, sometimes they're at different heights. Is there a reason that they're set off differently sometimes, or is it just how they set up the chiller?
Pretty much, Sean. I think it's just how much it's typically, if I can get back to my right screen here. Let's go back to that one picture. Usually what you're trying to do is create or to minimize floor space. So you can sit the condenser and evaporator tube side by side. Sometimes you will see that, but if the configuration of the compressor allows for them to overlap the condenser a little bit, that basically is you're just shortening up the width of the chiller by having those cylinders overlap in a vertical. So there's no engineering reason that they have to be different heights. I think it's typically more just to try to minimize the footprint.
All right, that makes sense.
Okay,
Yeah, thank you.
my pleasure. Anyone else? All right. Well, if you ever do have any questions about this stuff, you know where to go. Don't be strangers.